Question 1 says simplify the square root of 4 over 81. One thing we want to know before we start off this problem is that the square root of some kind of fraction, square root of any fraction, is the same as the square root of the numerator, the square root of the top of the fraction, over the square root of the denominator, the square root of the bottom there. So we can take the square root of a fraction and split it up and think of just the square root of each part of our fraction. That's a property of square roots that we're going to use here. So for this one here, we can then think of this as square root of the numerator, square root of 4, over the square root of the denominator, square root of 81. It's convenient to think of it that way because we know the square root of 4. The square root of 4 is 2, because 2 times 2 gives us 4. And we also know the square root of 81. It is 9, because 9 times 9 gives us 81. So our answer here is 2 over 9, 2 9ths, and that is answer choice A. Question 2 says use the product rule to simplify the expression. So the product rule for radicals and for square roots here gives us that the square root of a number times another number, square root of a product, is equal to the square root of the first number times the square root of the last number. It's a property of radicals we have there. Okay, so we can look here. Let's look at each part. The square root of 20. This product rule is going to help us simplify. If we could find some sort of perfect square that we know that is a factor of 20, some sort of perfect square, a number that we know the square root of that is a factor of 20 or that goes into 20 evenly. Maybe we can see that 4 is a factor of 20, and so I'm going to go ahead and split this up, this square root 20. I'm going to make this square root 4 times square root 5. We can do that because that follows our product rule here. 20 is 4 times 5, so we can split it up as the square root of 4 times the square root of 5. And here, so we also look at the square root of 24. We look at the number 24, and we say, well, can we think of a perfect square that is a factor of 24? Well, 4 just happens to be a factor of 24 also, so we could make this, since 24 is 4 times 6, we could make this the square root of 4 times the square root of 6. Okay, so now we can look at simplifying our perfect squares. We know the square root of 4. The square root of 4 is 2. So this is 2 times the square root of 5. And then we also know here, again, we have square root 4, so that becomes 2. So this is 2 times the square root of 6. We'll just write it 2 square root 6. And now we look at simplifying this further. We look at just our whole number parts here, the 2 times the 2 outside of the radical, so 2 times 2, that would give us 4. And now we can look at sort of going backwards with our product rule. I have the square root of 5 and the square root of 6. So instead of having those separate, using our product rule and now going the other way, having 2 separate square roots, we can write those as one root, one radical, and write the product underneath. So 5 times 6 would give us 30. And so we have 4 square root 30 as our answer after we simplify. And that is answer choice B. Question 3, we want to simplify this expression. We assume all the variables are non-negative real numbers. Okay, so we look at this first term here. We have a 3 on the outside, so this is 3 times the square root of 75xy squared. So we want to look at anything that might be a perfect square that we could separate out and simplify easily. So let's looking at the first term. So if we have 3 square root 75 xy squared. So let's look at each individual part and see if we know a perfect square that goes into any of these parts here. So if we look at the 75 here, 75 has a perfect square. 25 goes evenly into 75. So we could think of the 75, we could think of that as square root 25 times, and 25 times 3 gives us 75. So we have square root 25 times square root 3. That's the same as square root 75. And then we also have square root x here. There aren't any squares here. This is just one x term, so we still have just square root of x. And now this y square actually happens to be a perfect square also. Y square is certainly a square. And so if we look at this here, we know this is 3. Square root of 25, this is a perfect square we know as 5. And we have just our square root 3 here. There are no perfect squares inside of this 3 here. We still have just our square root x here, no squares in that. This is a perfect square. Y square is certainly a perfect square, and that becomes y, because y times y would give us y squared. So this first term here becomes 3 times 5 is 15, and we also have a y outside of the radicals here, so we'll write 15y. And then square root 3 times square root x, using our product rule, we could just write that as square root 3x. Okay, so we've simplified the first term here. Now let's look at the second term here. So we want to see if we can simplify 7y times the square root of 12x. So we look first at our 12 under the square root here, under our radical sign. So we see that 12 is actually, if we think of pulling a perfect square out here, 12 is the same as 4 times 3. So I'm going to split up my 12 as square root 4, square root 3. And then we also have a square root x there. So we've sort of broken it up into pieces. And we broke 12 up as a perfect square that we know. We know the square root of 4. So this becomes 7y times 2 times square root 3 times square root x. Okay, so now our 7 times 2, we would get 14y out here. And then square root 3 times square root x, we're going to get square root 3x there. Alright, and now we look at the last one. So we have a negative 2 square root of 27xy squared. So we're looking for, first we look at the 27 and we see, is there something that's a perfect square that goes evenly into 27? And there is. 27 is 9 times 3. 27 is 9 times 3, then we can turn it into the square root of 9 times the square root of 3. That would give us 27. And then as we did over here with xy square, we see we have xy square again, so this is going to become square root x. This is going to become square root of y square. And so now we look here, we know the square root of 9. It's a perfect square there. So the square root of 9 is 3, so this becomes negative 2 times 3. And then times all this stuff here, so times square root 3 times square root x. And since we see that this is a square here, this is a perfect square, y times y will give us the y square underneath, so that can be simplified to y. So now this becomes negative 2 times 3, which is 6. We also have a y outside, so negative 6y. And the square root 3 times square root x is again going to become square root 3x. So now these are all the same type of term, if you'll notice. This is a square root 3x term. This is a square root 3x term. This is a square root 3x term. So we have all the same radical, which makes that a like term. And so now we notice we also have y's as part of each term here. So we have 15y square root 3x plus 14y square root 3x. So between those two, that would give us 29y square root 3x. And then we would subtract 6y square root 3x. So we'd have 29y square root 3x minus 6y square root 3x. So 29y of those minus 6y of those would give us a total of 23y of those. So 23y square root 3x. And that is our answer. Answer choice D. Question 4 says simplify. Again, Again, we assume all the variables are non-negative real numbers. So we're going to look at this radical. We have the square root of 24x to the 7th y to the 4th. We're going to look at each part and see if there are perfect squares that we can recognize and pull out that we can simplify later. So if we look at this, let's start looking at the 24. So maybe we see that 24 is 6 times 4. And that helps us because we know the square root of 4. 4 is a perfect square, so that helps us. And here we have x to the 7th. So that's x being multiplied by itself 7 times, basically. We have 7 copies being multiplied. So instead of x to the 7th, I want to think of all of the squares that I could make with 7 copies of x. So maybe we could turn x to the 7th into x squared times x squared. That would be 4 copies of x there. Times x squared, another x squared. That would give us 6 copies of x. So we'd have 1 left over, so we could say just times x there. So again, we still have 7 copies of x being multiplied. Okay, so now we look at the y to the 4th, and we see what are some perfect squares we could make with that. Well, y to the 4th, that's 4 copies of y, so we could certainly make a pair of y's, y squared, and then we'd have another pair left over. We'd still have 2 left, so we could make another y squared out of that. Okay, so each of the perfect squares we know then can simplify outside of the radical as what we know the square root of that to be. So we don't know the square root of 6, so we'll go ahead and leave that underneath there. We do know the square root of 4. The square root of 4 is 2, so we're going to pull a 2 out there. Alright, and then we have the square root of x squared here, so we have our x squared here, and we know that that's a perfect square. And so we have an x outside. And each of these x squares here is going to give us an x outside. So we have times x, because the perfect square that gives us each of these x squares happens to be x. And now we look at, we have an x by itself that is not a perfect square, so we're going to need to leave this under the radical sign. So we'll leave that and move on. The next one, y squared, is a perfect square, and we say, well, what times itself gives us y squared? And the answer is y. And so since that's a perfect square, then that comes out as y. And so now this last y squared, same thing there. This is y times y. So we can pull y out. And so now we look at all of the things we had left that we couldn't pull out. And we couldn't pull out 6, and we couldn't pull out x, so those terms remain underneath our radical. And now we kind of want to simplify what's going on out here. We have 2 times, we have 3 copies of x here, also known as 2x to the 3rd, and we have 2 copies of y out here, also known as y squared. So 2x to the 3rd y squared, and again, nothing can be pulled out here, so we leave this square root 6x there. We leave the 6x under the radical. And that's as simplified as we can get. 2x cubed y squared, square root 6x, and that is answer choice E. Question 5 says simplify. We have 3 times the square root of 7 over the square root of 2. The reason we want to simplify this fraction, in math generally we don't want to leave any type of radical in the denominator of a fraction. So since we have a radical expression here in the bottom of our fraction, in our denominator, then we want to do something that's going to simplify so that we don't have a radical in our denominator. And we call this process, we call this, because this is called an irrational number when we have the square root here. So we call this process rationalizing the denominator. In other words, we don't want any type of radical, square root, any other type of root symbol in the denominator of our fraction. And the way we do the rationalizing of the denominator when we just have a single term, single radical in the denominator here, is we need to just simply multiply by that radical. And if we do that on the bottom to keep this fraction the same value, we have to do the same thing to the top, otherwise we're changing the value here. And the reason that that helps us is because we know that the square root of 2 times the square root of 2, by our product rule, the square root of 2 times the square root of 2 would give us the square root of 2 times 2, which is the square root of 4. And we know the square root of 4, right? That is 2. Okay, that's another property of square roots, right? The square root of a number times itself is going to give us that number. So we get 2 on the bottom here. And now we have 3 square root 7 times square root 2. So here, using the product rule again, we're going to have to multiply 7 and 2. And so we're going to get 3 times the square root of 7 times 2, which would be 14. So 3 square root 14 over 2. And that is answer choice B. Question 6. We're simplifying. We have 4 times the square root of 3 times this quantity here, and the quantity has square root 3 plus 7 square root 15 in here. So we have a number outside of a quantity. We're going to need to distribute this number here. So first we take 4 square root 3 and we take it times the first term in here. So we end up with 4 square root 3 times square root 3. Alright, then we have plus for the next one, and so we have to take this term times this term here. So now we have 4 square root 3 times 7 square root 15. Okay, now we have 2 separate terms here we want to look at, trying to simplify each term. So 4 square root 3 times square root 3, we know by the product rule for these radicals, square root 3 times square root 3 should just give us a 3. If we have the square root of a number times itself, it's going to give us that number. So this becomes 4 times 3. Square root 3 times square root 3 becomes 3 here. Alright, plus, now we need to look at the separate pieces here. Here on the outside, our numbers outside, we have 4 and 7. So 4 times 7 is going to give us 28 on the outside there. And then square root 3 times square root 15, our product rule tells us we can multiply these numbers, and that's going to give us square root of 45. Okay, so we have 4 times 3 plus 28 times square root 45. We know, obviously, 4 times 3, this is going to give us 12 here. And then we have plus 28 square root 45. So we want to make sure that now that we've combined these together, that square root 45 is as simple as it can get. So we think about, with 45, are there any factors of 45 that are a perfect square that we know? And if we think about it for a second, we may see that 45 equals 5 times 9. And we know that 9 is a perfect square. We know the square root of 9. So we want to split this up. So we're going to make this 28 square root 5 times square root 9. Okay, and the reason we do that is, well, we know the square root of 9, and we know that this is actually equal to 3 here. So we have 12 plus, so now our numbers on the outside, 28 times 3, that's going to give us 84 when we multiply that. And then we have square root 5, so now our radical is fully simplified there. 12 plus 84 square root 5. We can't combine these terms. These have to stay separate terms, because this term has a square root 5. This term does not have any square root at all, so they don't have matching radical expressions. The only way we can add things together as like terms is when they have a matching radical expression, and these do not. So we would leave this separate, 12 plus 84 times the square root of 5, and that is answer choice B. Question 7 says simplify. Here we have the cube root of negative 64. So a cube root of a number, we have a cube root, that means we want to find the number that when multiplied by itself using 3 copies would give us the number we have underneath, which is negative 64. So we're looking for a number that if we multiply that same number, if we multiply 3 copies of that same number times itself, it would give us negative 64. Well, first let's look at the negative sign. So first we look and say, well, what would we need if we had 3 copies to give us a negative? Well, we couldn't get it with a positive number. A positive times a positive times a positive would certainly give us a positive number. So we would need a negative here. A negative times a negative would give us a positive, but then times a third negative number would change that sign back to a negative. And now we're looking for something that would multiply 3 times to give us 64. And if we think about it for a minute, we can probably see that 4 times 4 would give us 16, but then times another 4 would give us 64. So again, let's check this. Negative 4 times negative 4, same sign would give us a positive, and 4 times 4 would be 16. And now if we take this positive 16 times this last copy of negative 4, a positive times a negative would give us negative, and 16 times 4 is 64. So it looks like negative 4 is the number we're looking for. So the cube root of negative 64 is negative 4. And that is answer choice A. Question 8 says factor 2 over 3 minus the square root of 6. Alright, so if we're looking to factor this, what we really need to do is we need to rationalize our denominator again. So we're going to be looking at rationalizing the denominator. And the way we do that is a little bit different than it was the last time we did this in one of the previous questions, because now we have 2 terms in the denominator. So instead of just multiplying by this square root 6 on the bottom, then we actually need to multiply by what is called the conjugate of the denominator. And the conjugate of the denominator is going to be the same as this 3 and square root 6, but instead of having a minus, instead of it being the difference of 3 and square root 6. So we're going to multiply by 3 plus square root 6. And that will help us rationalize our denominator. Okay. So we're going to multiply by 3 plus square root 6. That'll help us clear the radical here. Whatever we do to the bottom of the fraction, we need to do to the top. And so notice our fractions here have more than one term in some places, so we want to make sure we think of distributing whenever distributing is necessary. Alright, so if we look at the numerator here, let's go ahead and distribute our 2. 2 times 3, that would give us 6 there. And 2 times square root 6 would just give us a 2 square root 6. Now on the bottom, we want to look at this here. So 3 times 3 is going to give us 9. 3 times square root 6 would give us a plus 3 square root 6. And then here when we distribute the negative root 6 here, times 3 would get a minus 3 square root 6. You can see that's going to help us cancel the positive 3 square root 6 that we had. And then negative square root 6 times square root 6. So negative times a positive would give us a negative there. And then square root 6 times square root 6, that is going to give us just the number 6 by the square root properties there. Okay, so we can see right here that our first and last term don't have any radicals, and our middle 2 terms, when we distribute, we get a positive and a negative of the same quantity. So multiplying by the conjugate really helps us clear out any denominator radicals we have. Okay, so here on top, 6 plus 2 square root 6, remember those must stay separate because they are not like terms. This has a radical, this does not. And down here on the bottom, so our plus 3 square root 6 and our minus 3 square root 6 are going to cancel. We're just left with 9 minus 6. That's going to give us 3 there. So 6 plus 2 square root 6 over 3. We look for a common factor of 6, 2, and 3. They don't have any common factors. So we would leave that as our answer there. 6 plus 2 square root 6 over 3 is answer choice C. Question 9 says solve the following equation. We have square root of 2x plus 1 equals x minus 7. So when we have an equation like this with variables underneath a radical sign that we're trying to solve for, first thing we want to do is get that radical or this square root here by itself. We can see this has already been done for us. We already have the square root by itself on the left side of the equal sign. And so now we want to work on getting rid of this radical, this square root here. And so we want to do the opposite of whatever square root is to get rid of that. And the opposite of square root is square. So to get rid of this radical, this square root here, we could square this side of the equation. And whatever we do to the left side, we want to do to the right side. So we would need to square the right side of the equation also. So we're going to see sort of what that gets us here. Notice I'm putting them in parentheses so I can notice if I need to distribute anything. Now one thing we want to make sure that we note here when we start using this method to solve is that when we square both sides of an equation, it is possible when we square both sides that we may get some type of false answers. Okay? So squaring both sides can give false answers. And so what we want to make sure is we want to make sure anything we get as an answer we think of just as a potential answer, and we need to go back and then check anything we get here. Okay, so let's move on, and so we see we have square of a square root. Those are opposites of each other and are going to cancel, just like add and subtract cancel each other, multiply and divide cancel each other. So here we are just left with the expression underneath the radical, which is 2x plus 1. And now maybe we can see on the other side here, this x minus 7 square is really going to need to become x minus 7 times x minus 7. We're going to have to distribute that into itself here. Okay, so x minus 7 times x minus 7. So first we distribute the x. X times x is x squared. X times negative 7 gives us negative 7x. And now we distribute the negative 7. Negative 7 times x gives us another negative 7x. And negative 7 times negative 7, we get a positive 49. Alright, and now we can see we have like terms that we can combine. So we have 2x plus 1 equals x squared minus 14x plus 49. Okay, now this has become a quadratic equation because our highest power of x is 2. We have an x squared term there. So this has become a quadratic equation, a lot like the stuff we would solve in chapter 6. So what we want to do here is to solve this equation with quadratic, get everything on the same side first. So let's move our 2x plus 1. So we'll subtract 2x and cancel that, and subtract 1 and cancel that. And we must do the same thing to the other side. Alright, so that's going to leave us 0, which is what we want on that side. And here we have x squared minus 16x plus 49 minus 1 gives us plus 48. Okay, and so now we would look at factoring the right-hand side like we would have done in chapter 6. Factoring, we're going to need, we look at, this is like a 1x squared, so we're going to need two numbers that multiply to give us 48. And that add to give us negative 16. So we're looking for two numbers that work there. We would regroup our middle term according to those two numbers, and the numbers happen to be, in this case, a negative 12 and a negative 4. Those would work. Would multiply to give us 48 and add to give us negative 16. So we are, let's scroll down here, and we would rewrite this equation as 0 equals x squared minus 12x minus 4x plus 48. Okay, so again, we're just using methods that we used earlier in chapter 6. So if you have any questions on how we're working this section here, you can see the section that talks about chapter 6. Alright, so now we look at the first pair here, and we look for greatest common factor. The greatest common factor of these two is x, and left over in the first term we have an x, and in the second term we have a minus 12 left over. So my x minus 12 must be a factor of the second pair, x minus 12, and we say what times x minus 12 would give us this second pair here, And we can see maybe we would need a 4, and we would also need a negative there. Negative 4 times x gives us negative 4x. Negative 4 times negative 12 gives us that. And so now we look at grouping our factors together. The outside terms become x minus 4 as a factor, and we have x minus 12 also as a factor. All right, and so now just from chapter 6, again, we use the multiplicative property of 0, which says that if I have two things multiplying together to get 0, that one or both of those things must be 0. So either x minus 4 is 0, or x minus 12 is 0, or both. So we want to figure out what x is for each of those cases. So we look at x minus 4 equals 0. Here, adding 4 to both sides is going to give us that x equals 4. And in this case, adding 12 to both sides is going to give us that x equals 12. All right, so our potential answers here are 4 and 12. Remember, we want to come back and check our answers, 4 and 12, because squaring both sides can give us false answers. So we have potential answers 4 and 12. And let's go back and check those. So if we look at the original equation, here I'm going to erase my markings so we can see what the original equation was a little better. So if we check 4, we would have the square root of 2 times 4 would give us 8 plus 1, so we would end up with the square root of 9 underneath there, equals, this x would become 4, because we're plugging in 4 to check, 4 minus 7. And so we want to see, the square root of 9 would be 3, but 4 minus 7 would give us negative 3. So our potential answer of 4 does not check, so 4 is not an actual answer that we want to say would be a good answer for this problem. So now we check our potential answer of 12 here, checking 12. So if we plug in 12, we'd get 2 times 12 underneath, which would give us 24. And 24 plus 1 would give us square root of 25, so we'd have 25 under there, equals, x is 12 again, so 12 minus 7 here on the right-hand side. And we know the square root of 25 is 5, and 12 minus 7 also gives us 5. So this one checks out okay. And we would say out of our two potential answers, 4 and 12, 12 is the only answer that checks here. So our only answer then is going to be 12. And that gives us answer choice D. Question 10 says simplify the quantity 2 square root 5 plus 3 squared. Okay, so again, remember when we have a quantity square, that is the same as having the quantity times itself. So we really have 2 square root 5 plus 3 times 2 square root 5 plus 3. And so now we want to distribute, or FOIL, these into each other here. So we look at 2 square root 5 times 2 square root 5. Well, the 2 times 2 part would give us 4. And the square root 5 times the square root 5, that would just give us 5. So we get 4 times 5 for our first term. All right, now we distribute the 2 square root 5 times the positive 3. So again, this is an outside term here, this 3. So 3 gets multiplied times the 2, which is also on the outside. And 2 times 3 gives us 6. And the square root 5 just stays square root 5 because there's no other radical to multiply it by. And now let's distribute the plus 3 here. So plus 3 times 2 square root 5. That's going to give us the same thing as the first term times the last term here. So we get another plus 6 square root of 5. And the 3 times the 3, both positive, so we would get a plus 9 there. Okay, so here we have, this would be 20 right here. So we have 20. We also have 9. Those are both terms that don't have a radical in them, so we can combine those as like terms. 20 plus 9 would give us 29. And now, these are both square root 5 terms. They have like radicals. So we have 6 square root 5 plus another 6 square root 5. So the total square root 5s we have is actually 12 of them. We have 6 of them here, 6 of them here. You can think of square root 5 as an object. We have 6 of them and 6 of them, so we really have 12 of them total. And so these are not like terms because one has a radical, one does not. 29 plus 12 square root 5. And that is answer choice B. Question 11 says solve the following equation. Square root 5x minus 4 plus 9 equals 3. So this question is similar to question 9 that we talked about previously. And remember, we said that the first thing we want to do whenever we're solving an equation that has variables under the radical is we want to try and get the radical expression by itself on one side of the equal sign first. So here we have the plus 9 hanging out here outside of the radical, and that's keeping it from being by itself. So we want to get rid of the plus 9 from this side. The first thing we're going to do is subtract 9 from that side. So we must subtract 9 from this side as well. And so here we're going to get the square root of 5x minus 4 equals, and here we get 3 minus 9 is negative 6. Okay, now in the previous one, we would say, well, we could square both sides, right, to get rid of the radical, which is what we did before, and then see what we get. If we look at this here, though, we have the square root of an expression equals a negative number. And in general, we say that a square root of something, when we take the square root of something, we consider it to be a positive square root. So the number over here should always be some sort of positive number. So if we're saying that the square root of something gives us a negative number, then that actually doesn't have a real solution. We generally, when we say square root, we're thinking of what positive number times itself will give us that expression there. So since we're saying the square root here is equal to a negative number, there actually isn't a real number solution that's going to work for that. So before we start squaring both sides and working everything out and going back to check our answer, maybe we just notice here that the answer is no real number will work for us. If we went the long route and we actually squared both sides and then we went back and checked our answer that we got, we would see that the answer doesn't check, and so we would again get no real number. But this is a shortcut here to notice that when we have a square root on one side by itself equals and a negative number on the other side by itself, there is no real number solution that's going to work for that. And so our answer choice here is E. Question 12 says simplify 3 plus square root 27 over 3. Well, first let's look at our radical here. We have the square root of 27, and so we want to see if we can simplify this part here. So we look at, are there any perfect squares that we know that go evenly into 27? And earlier in the test, I think we saw this one as well. So 27 is 3 times 9. So we could think of this as equal to 3 plus the square root of 3 times the square root of 9. Simplify that out and we can see our perfect square here. So we know the square root of 9. The square root of 9 is 3 here. So we get 3 plus, this would become square root 3 times 3. So we're going to get 3 square root 3. I'm going to write it that way. Over 3. And now maybe we can see that they all kind of have a common factor of 3 here. If we can't see it, because this fraction is all over a one-term denominator, so maybe let's split it up into separate parts. So let's take the first part, so 3 over the denominator, plus, now let's take the second part, so 3 square root 3 over the denominator. We can do that when we have just a single term in the bottom. And so now if we look here, 3 over 3, we know 3 divided by 3 is going to give us 1. And again, 3 square root 3 over 3, if we're multiplying by 3 and then dividing by 3, then we really only have 1 square root 3 here. So we just have square root 3. And 1 plus square root 3, that's as simple as that gets, because this is a radical term here. This does not have a radical. So 1 plus square root 3, and that is answer choice A. Question 13 says simplify 6 square root 32 over 18 square root 8. So first thing we see on the bottom in our denominator, we have a square root 8 here. We have a radical. And so we might say, well, the first thing we want to do is rationalize the denominator. But let's hold off on that and wait on rationalizing the denominator. And let's look at maybe breaking this up a different way before we start multiplying numbers in and making the numbers even larger. Let's look at, this is really 6 times the square root of 32. And the bottom is really like 18 times the square root of 8. Okay? If we have something on top multiplying by something else, and something on bottom multiplying by something else, let's go ahead and split this up into 6 over 18 times square root 32 over square root 8. Now we can do that because think about when we multiply fractions, if I were to multiply what I just have here back together, I would multiply the numerators together, the 6 times square root 32, I'd get back what I had originally. And on the bottom I would take the denominators and multiply, because with fractions we multiply straight across whenever we multiply. So that's okay, we can do that and split it up into those two separate pieces there. So now let's look at what we have here. Well, this is really 6 over 18 would reduce to a third, right? Because both of these numbers are divisible by 6. So we could divide each part by 6, leaving us 1/3. And now let's think about going the opposite way of what we did at the very beginning of the test. When we have the square root of a numerator, square root of a denominator, maybe it might make it easier for us to think of it as the square root of 32 over 8 as one big fraction. And the reason that would help us is because we actually know 32 divided by 8. 8 goes into 32 evenly there. So we look at having, so we have 1/3 times the square root of 32 over 8 is really 4. And we just happen to know the square root of 4. 4 is a perfect square. And so we know the square root of 4 is 2. And so we have 1/3 times 2. If we're having a hard time seeing that, we can write our 2 as a fraction. Think of it as 2 over 1. And we can see when we multiply straight across with the numerators and the denominators, we're going to get 2 over 3, 2/3. And that is answer choice C. Question 14. Simplify. Assume all variables are non-negative reals. So we have the square root of 27x cubed over 2. So first we look at this and see, is there anything we can simplify in its present form? 27 over 2, nothing simplifies there. There's no common factors. We just have x's in the numerator here. Nothing to simplify anyway there. So let's go ahead and split this up and see if we split it up, maybe that will help us to simplify more. So let's think of it as the square root of the numerator, so square root of 27x cubed over the square root of 2. Maybe that will help us somehow. Okay, so if we look at the top here, maybe we can think of pulling out our perfect squares like we've been doing. So we look at 27 and we say, well, what is 27? 27 happens to be 3 times 9, so I'm going to split it up into 3 and 9 because we know that 9 is a perfect square. And can we make any perfect squares out of x cubed? And we can. We could make an x square with x cubed, and we'd have an x left over. We still have our 3 copies of x here. Okay, so we have that on top. Let's go ahead and leave our square root 2 on the bottom in our denominator here. So we can see this is going to be square root 3. That stays here. That's not a perfect square. Square root 9 is a perfect square. Square root of 9 is 3, so we're going to go ahead and bump that out. So that becomes 3 on the outside. X squared is a perfect square. That's x times itself, so we're going to go ahead and bump that out as an x. And this x by itself is not a perfect square, so we have to leave that underneath. So we left the 3 underneath, and we left the x here. So we still have 3x underneath our radical, and we have that over the square root of 2 still. So now we've pretty much simplified our roots as much as we can. Our radicals are simplified. And notice now we still have this square root 2. We have this radical in the denominator, so we want to rationalize our denominator. And so what we need to do is we need to multiply the top and bottom by the square root of 2. Rationalize our denominator. Okay, so square root 2 times square root 2 in the denominator is certainly just going to give us 2. And now this square root 2 on top is going to multiply by this square root 3x, and 2 times 3x would give us a square root 6x. And don't forget that outside we have the 3x there. So we have 3x times the square root of 6x over 2. Nothing will cancel here, nothing in common factor-wise on the outside. So we'll leave that answer, 3x square root 6x over 2, and that is answer choice C. Question 15. Again, we're simplifying. We have this expression here. So we cannot just cancel the terms here, even though we have square root x over square root x, and we have 5 over 5. We cannot cancel those. Again, in order to cancel something from a fraction, it has to be a factor. Square root x is not a factor of the top, it's just a term in the top, just like it's a term in the bottom here. So we cannot just cancel these like terms that we see written directly over one another. We have, again, like before, we have this expression where there's a denominator with a radical in it, and it's more than one term in this denominator. So remember, like we did before, we want to multiply by the conjugate of the denominator. And the conjugate of the denominator here is actually going to be square root x minus 5. Remember, we changed the sign here. If we're adding, then we change it to subtract. If we're subtracting, we change it to add. So the conjugate of this denominator that we want to multiply by then is going to be square root x minus 5. Again, we're always looking at the denominator to figure out what conjugate we need. Okay, so we must multiply the top by the same thing. We just happen to get the same thing on top. Alright, and so now again, remember, we want to look at, when we multiply by conjugate, we want to think of distributing. So first let's distribute the top. So square root x times square root x. So square root of something times itself is going to give us what's underneath, so it's just going to give us x. X times negative 5 would give us, square root x times negative 5 would give us negative 5 square root x. And now we distribute the second term, negative 5 times this square root x is going to give us another negative 5 square root x. And negative 5 times negative 5 would give us plus 25. And now we look at the bottom. So here we see in the denominator, again, square root x times square root x. We're going to get just x there. And remember what happened last time we used conjugate, when we take the inner and outer terms here. So the inner terms we're going to get a plus 5 square root x. The outer terms we're going to get a minus 5 square root x. Those are going to cancel. Whenever we write those down, those will cancel out because they're opposite. And then the positive 5 times a negative 5 gives us a negative 25. So we have x minus 25 on the bottom. Okay, so now we look at, notice we have some like terms on the top here. We want to put those together, combine those like terms. These are both square root x terms. They have matching radicals. So we have negative 5 of them here, minus another 5 of them, so we really have negative 10 of those. So we can combine that as a like term. Again, these are not like terms in the denominator on the bottom here, so that stays x minus 25. And nothing in common factor-wise there, so that would be our final answer. And that is answer choice A. Question 16, they want to simplify the cube root. Notice we have a 3 out here. The cube root of 5 over 4. So remember, the cube root is something that multiplies by itself 3 times. We have 3 copies being multiplied to give us that number. So we cannot simplify the 5 over the 4, so maybe let's use a property of radicals here, and let's change it to, now remember it's a cube root, so this becomes the cube root of the top, so cube root of 5, over the cube root of 4. And so now we can look and say, well, is there anything we know, if we multiply it 3 times, do we get 5? And I don't think there are any numbers maybe we can see there. And certainly if this was a square root on the bottom, so we know the square root of 4, but we don't know the cube root of 4. So it looks like our only option to simplify here now is to try and rationalize our denominator. Alright, so a little bit different here. If we're going to rationalize our denominator and get rid of the radical, what we would really need to multiply by is, if we had another copy of, let's say, the cube root of 4, and we multiplied by that on the top and the bottom, would that be sufficient to rationalize our denominator? Well, no, because now it's a cube root, so in order to rationalize, to get rid of the radical, we would need 3 of the same thing to rationalize our denominator here. So we need to multiply by another copy of the cube root of 4 in order to have enough to give us what we want. Okay, so now the cube root of 4 times the cube root of 4 times the cube root of 4, 3 of those, that's just going to give us the number 4 there. Okay, and then on top, now we will have the cube root of these numbers multiplied together. So 5 times 4 would give us 20, and then times another 4 would give us 80. So let's go ahead and write. So we're going to have the cube root of 5 times 4 times 4. And if we simplified that, we said that would be the cube root of 80 there. Okay, so now we want to look and see, is there any other simplification we can have? And we want to see, is there some sort of cube root that we might know, a perfect cube, in other words, that goes into 80. And so maybe we start thinking of the factors of 80. So let's look at, because I think that might not be easy to see. So let's look at factors of 80 and see if any of those are perfect cubes. So we have 1, and 80 is even, so 2 goes in. 3 doesn't go into 80, but 4 does. 5 also goes in. 6 and 7 do not go in. 8 goes in. And 9 does not go in. 10 goes in as well. Okay, and if we look at, let's look at some of these. So 1 times 80 would give us 80. 80 is also a factor. 2 times 40 would give us 80, so that's also a factor. 4 times 20. And 5 times 16 would also give us that. And again, 8 times 10. So here we have all of the factors, and we look at, are any of these cubes? Are they perfect cubes? In other words, some number times itself 3 times, using 3 copies would give us that. Well, the only one that works here really is 8. 8 happens to be a perfect cube because 8 is 2 times 2 times 2. So we know the cube root of 8. In other words, the cube root of 8 is going to be 2, because 3 copies of 2 being multiplied will give us 8. So let's go ahead and pull the 8 out and see if that helps us here. So that gives us the cube root of 8 times the cube root of, so we would need 8 times what would give us 80, and that's 10 there, over 4. Okay, so here we have the cube root of 8 times the cube root of 10 over 4. And remember, we said that this is going to be 2. We know the cube root of 8 is 2. So what we really have there is 2 times the cube root of 10 over 4. And now we can see we have a fraction that has 2 over 4. And we know that 2 over 4 is the same as, 2/4 is the same as 1/2. In other words, we can reduce these having a common factor of 2. So we really get a 1 on the top and a 2 on the bottom if we reduce that to a half. So we just get 1 cube root of 10 on the top, or cube root of 10. And on the bottom we get 2. And so now that's as simplified as we can get there. So we have the cube root of 10 over 2, and that is answer choice E. Question 17 says, simplify 3 square root 54 minus 4 square root 24 plus square root of 150. Okay, so we want to look at first reducing these radicals to the lowest term radical we can possibly get there. So first let's look at the square root of 54 and see if there's anything we can reduce there. So some of these are large numbers, so maybe we think about listing the factors. So let's go ahead and list out the factors. So the first one, let's do 54 first. So the factors of 54, we have 1 times 54, and we have 2 times 27, and 3 goes into 54 also. 3 times 18 would give us 54. 4 does not go in, 5 does not go in, but 6 goes into 54 9 times. 7 does not go in, and 8 does not go in as well. So here, these are the possible factors of 54. And let's go ahead and list all our possible factors of 150. A few more of those here. Okay, so we know 1 times 150 would give us that. It ends in a 0, so we know it's divisible by 2. 2 times 75 would give us that. This is divisible by 3. 3 times 50 would give us 150. It's not divisible by 4. 5 does go in. 5 times 30 would give us that. 6 happens to go into that. 6 times 25. 7 does not. 8 does not. 9 also does not. 10 happens to go in, though. 10 goes in 15 times. Okay, and so now we have all the factors here of 150. Let's sort of look at anything that might be a perfect square. Looking at 54 here, we can try and find a perfect square. We have one here. 9 is a perfect square. And so let's go ahead and make this 54 then. 3 square root 9 times the square root of 6, since we have those factors there, minus, we've already done 24, and we remember maybe that the perfect square inside of 24 is 4, because 24 is 4 times 6. So this becomes 4 square root 4 times square root 6. Alright, and then we have plus 150, so let's look for the biggest perfect square we can find in here. None of these down the left side are perfect squares, but if we see over here, 25 is a perfect square. We should know the square root of 25. So let's go ahead and make 6 times 25 would give us 150, so let's go ahead and make this square root 25 times square root 6. Okay, and so now again, we know the square root of 9. The square root of 9 is 3, so this is 3 times 3 square root 6. Minus, again, we know the square root of 4, so that becomes 4 times 2 square root 6. And we know the square root of 25, and that becomes 5 square root 6. Okay, let's simplify our multiplication. 3 times 3 is 9. 4 times 2 is going to give us 8 of those, and then plus 5 here. So now we look at, these are all like terms because they all have matching radicals, all square root 6 terms. So we have 9 of them minus 8 of them. 9 minus 8 would give us 1, plus 5 more of them. So 1 plus 5 would give us 6 square root 6s. And that is our simplified answer there, 6 square root 6. And that is answer choice B. Question 18, simplify. So we have the quantity 6 square root 3 plus 2 times the quantity 5 square root 3 plus 1. So you can see this is going to just be a distributing problem or a foiling problem here. So let's distribute the 6 square root 3. 6 square root 3 times this first term over here. So that's going to give us 6 times 5 on the outside. And then we're going to get square root 3 times square root 3. We'll come back and simplify that later. So now we have 6 square root 3 times the plus 1 here. So times 1 is just going to give us 6 square root 3 there. Alright, and now let's go ahead and distribute our plus 2. So plus 2 times 5 square root 3, so 2 times the 5, that's going to give us 10 square root 3. And then 2 times 1 is just going to give us a positive 2 there. Okay, so now let's simplify this first term up here. 6 times 5 is going to give us 30 times, and square root 3 times square root 3 is just going to give us 3. Okay, and now if we notice here we have matching radicals, so these are like terms. We can add these together. We have 6 square root 3s plus 10 square root 3s. That's going to give us a total of 16 square root 3s. And plus 2. So now this, if we look at 30 times 3, that's going to give us 90, and that's going to match our plus 2 at the end. Those are like terms because there's no radical there. So 90 plus 2 would give us 92, plus we have 16 square root 3. And these have to stay separate. They're not like terms, so this is simplified. 92 plus 16 square root 3. Answer choice C. Question 19. Solve the following equation. Square root of 7x minus 3 equals 5. Okay, so here we already have our square root expression by itself on one side of the equal sign, and this time it does not equal a negative number, so we're okay to go ahead and solve this here. We might get an answer that actually works for this here. In fact, we should. So to get rid of square root, the opposite of square root is square, so we're going to square this side to get rid of that radical. And since we're squaring that side, we have to square this side. Okay, so now we look at the square root and the square canceling, just leaving us 7x minus 3 equals 5 squared, or 5 times 5, which is 25. And now this just becomes a linear equation that we can just solve easily for x. So first we get the x term by itself, so we'll add 3 to both sides, and that gives us 7x equals 25 plus 3 is 28. Now we just divide by our 7, so we can just have x, and that's going to give us x equals 4. Now just to make sure, since we squared both sides, let's go back and look at our original equation and just make sure that our answer works here. So plugging in 4, so we're going to check our answer of 4. So we have the square root of 7 times 4 minus 3, and we want that to equal 5. 7 times 4 is going to give us 28. 28 minus 3 would give us 25 under there, and we know that the square root of 25 is 5, so that definitely checks. So our answer, x equals 4, and that is answer choice C. Question 20 says, find the value of x in the right triangle. So here we have a situation where we're solving for the length of a missing side in a right triangle. And when that's the case, we want to use the Pythagorean theorem. The Pythagorean theorem gives us a formula where we can find the missing side that we don't know in a right triangle. And the Pythagorean theorem tells us that a square plus b square equals c square. Okay, so well, what does this really mean? Well, a and b are the sides of our right triangle that happen to touch the right angle. Okay, so here we can see this little square is denoting our right angle, or our 90-degree angle. Okay, so a and b are the sides that touch the right angle. Always want to remember that. And C is always what we call the hypotenuse of the right triangle. C is the hypotenuse. And the hypotenuse is the side that does not touch the right angle in the right triangle. So here we can see that this diagonal side here is going to be our hypotenuse. Okay, so if we look at this, A and B, the sides that touch the right angle, that's going to be 5 and 12. So maybe I call this side that is length 5, maybe I call this one A, maybe I call this one B. You could do it the other way if you wanted, as long as you choose those two sides. Okay, and then so this is obviously hypotenuse because it does not touch the right angle, so we're going to call this side the C side. And now let's just sort of plug into our formula that we have here, our Pythagorean theorem. So A is 5, so 5 squared would be how we start out here. And then plus B squared, and B is 12, so plus 12 squared is going to equal C squared, and C is our hypotenuse, and that has length x, so we're going to say x squared. So we just plugged in for A, B, and C, we plugged in 5, 12, and x into our Pythagorean theorem. Okay, so now here we just want to start simplifying and trying to figure out what x is. So we know 5 squared, that's 5 times 5, which is 25. And we should know 12 squared is 12 times 12, which gives us 144. and that equals x squared. And so now let's simplify our addition here. 25 plus 144 is 169 equals x squared. Okay, and so now we want to look at some number times itself, giving us 169. Okay, and maybe we can't see what that number is right off the bat, and that's okay. So we can sort of do the opposite of what we did before. We have an x square over here, and we want to know x. So how do we get rid of square? Well, we want to do the opposite of what square is. And remember, square was the opposite of square root. We used square to solve our square root equations. So if we want to do the opposite to get rid of square, we could square root this side. Square root and square cancel each other. And we could do the same thing. We would have to do the same thing on the other side. Okay? Now there's a particular thing here. When we square root a square, that's going to cancel. That gives us x. But so now think about, if we were saying x squared gives us 169, well, it could be a positive number, right? A positive times a positive would give us 169, but it could also be a negative number. A negative times a negative still gives us a positive number, so we could still have a negative number times a negative number, giving us a positive 169 here. So whatever number we have here, in other words, whatever square root of 169 is, we have to really have the positive case and the negative case there. And if we take the square root of 169, we get 13. So positive 13 and negative 13 would actually work here. If we squared 13, we'd get 169. If we squared negative 13, we would also get 169. So now we look back at our original problem here and we see, well, we're talking about x being the length of a side of a triangle is what we're talking about. So if we say x is 13 or x is negative 13, we look at, well, certainly x being negative 13 doesn't make a lot of sense in this problem. If we say x is negative 13 units long, whether it's inches or feet or whatever this is, it doesn't make any sense because this is a physical distance here. Okay? We can't say, well, we have a length of negative 13. So really, our answer choice here should just be the positive case. X should be a positive 13. That makes sense. It could be 13 units long if it were positive. So here we say that x equals 13, and that is answer choice A.